Hi, it's Mr. Duffy. Welcome to physics. Today we're going to be talking about graphing constant acceleration. We've been talking a lot about acceleration in general, but what we want to do today is show how to represent that with position time graphs and velocity time graphs. Let's go ahead and get started. Acceleration is the change in velocity over the change in time. And we can calculate that using an equation, but we can also show it using our graphs. The one graph we've talked about so far is a position time graph. A position time graph has the position of the object and on the y-axis, and again the time on the x. This is nothing new, we've covered this already. But what we've covered with it so far is only objects that are moving with a constant velocity, in which case those show a perfectly straight linear line. So the question is, I guess, what does acceleration look like on them? Well, on a position time graph, acceleration would be a curved line. Curved line shows acceleration on a position time graph because the distance changes with time. It's not covering equal distances in equal amounts of time. There are different curves, obviously, depending on what the object is doing, if it's speeding up or slowing down, if it's speeding up in the negative direction or slowing down in the negative direction. Again, those those different variables will represent different curved lines, but still, everything on a position time graph that shows acceleration is going to show a curve. And we can kind of see this when we're looking at a picture of an object. I've showed you this picture as well. It's a billiard ball being dropped, and it takes a picture of the billiard ball every 1/10 of a second. What we can see again is we notice that the distance increases with time. The spacing between the billiard balls increases with time. And so a graph would show increasing amounts of position in in that time interval. Okay? So again, a curved line showing acceleration. We know that slope is really important when we're talking about a position time graph because slope shows us the velocity of an object. When we're talking about a straight linear line, we can find the slope by doing rise over run. And that's fairly simple. But how do we find the slope of a curved line? Well, there are two different ways to do that. To find the velocity using the slope of a curved line, we can find it in two different ways. We can find it by finding the average velocity over the whole entire trip. Or again, what would be, I think, more relevant would be to find the instantaneous velocity at a particular instance in the trip, especially if the velocity is changing throughout that trip. Let's start off with talking about the average velocity and looking at it over again, the entire motion of the object. What we would do is we would find what is the initial position, what is the final position, and we would connect those 2 points with a linear, eh, fairly linear. Well, it is linear, but I missed the points. Line. From there, we can find the rise, the change in my y values, which would be the change in position, and then the run, which would be the change in my x values or my change in time. Find rise over run, that's my slope, that's my average velocity over the entire trip. Average velocity is really, I don't think, very useful. Um, it is something we can find, but it isn't super useful for something that's accelerating. Because when something's accelerating, it's changing its velocity. So we might want to know more of what was the velocity at the beginning of the trip and what was the velocity at the end of the trip. Again, what was kind of going on. And to do that, we kind of have to draw what's called to find that we want to find the instantaneous velocity. And to do that, we have to draw what's called a tangent line. A tangent line is a line that only passes or touches a curve or a circle or something at one point. And so that tangent line will be a straight line, and that will allow us to find the slope of that line at that particular point that it touches the curve. We would still do it in the same way. We still find the rise and the run, change in my y positions, the change in my position, and the change in my time And by doing rise over run for the tangent line, I could find the instantaneous velocity, how fast it was going at that particular time, let's just say like 3 seconds. That would again be a lot more useful. If I use the same method and find another tangent line, find the rise and the run here, I can find the speed at a second time, maybe 5 seconds, and I can compare the velocities. I can see again that it's slowing down. I can tell that just by the tangent lines themselves because one has a steeper slope and one is less steep or shallow. But again, I can then get values for how fast it was going at those particular times. I think that's more useful than what was the average velocity over the entire trip. Okay, but different ways of solving for velocities. Now, what I want to introduce you to now, we've talked about position time graphs in the past. It is obviously new that they are curves when we show acceleration, but what is now going to be new is a new type of graph called a velocity time graph. And as you might be might make sense, a velocity time graph shows the speed or velocity on the y-axis and time on the x-axis. Now, why I say speed or velocity, speed is again just an amount, but the magnitude of it being positive or negative tells us the direction. So that makes it a vector quantity. Okay, so again, that goes on our y-axis, and being positive or negative tells us the velocity as well. So it's a velocity time graph or speed time graph. Um, anyways, now a speed time or a velocity time graph can have negative values as well. A lot of the times, again, we might just look at the positive areas, but that's not always going to be the case. We do want to look at negative areas because, again, that means the positive and negative mean direction. Which direction is it moving? And we can have negative positions and negative velocities. So, velocity time graphs can also have negative areas. So, what can a velocity time graph show us, or speed time graph? What can they show us? Well, there's the obvious things. It can show us the speed of an object at a particular time. Okay, that would be useful. By looking at the graph as well, we can generally tell what the object is doing. Is it speeding up? Is it slowing down? Is it moving at a constant velocity? Is it at rest? Just by looking at the graph, we should be able to tell what the object is doing. There are some other subtle things then as well that we could tell from a velocity time graph. We can find the acceleration. Now, I will go over how to do that a little bit later in this video. But again, that is something that we can tell from this graph. And another thing that actually is very interesting is we can find the distance traveled. I will actually cover that in a future lesson. Okay? So, basically, again, position time graphs were super useful at telling us information about what's going on. But velocity time graphs can do very similar. We can tell, again, a good amount of information. We can analyze an object's motion by looking at a velocity time graph as well. Okay, let's take a look at a velocity time graph and let's try and analyze what this object is doing. Okay, to do that, we could analyze the whole motion and again, what is it doing over the entire trip? But I think it's more important to focus on what is it doing at different portions of the trip. We're going to take a look at 0 to 10 seconds, time frame 10 to 15 seconds, 15 to 30 seconds, 30 to 40 seconds, and 40 to 55 seconds. I think those are the most relevant, most important time frames in this graph to look at. So let's start at the beginning. At 0 seconds, it's starting its motion. And what it's doing, if we watch the graph, we can see that the speed is increasing. Speed is going up, going from 0 meters per second, meters per minute, to 60 meters per minute. So I'm going to write it right on the graph. Speeding up. The next portion of the graph that we come to is a horizontal portion. No slope at all. Now, if we remember from position time graphs, something that had no slope meant that it was at rest. But what I want you to realize here is that it does not mean that. At 10 to 15 seconds, this object is moving with a constant speed. The speed is staying the same. It is staying at 60 meters per minute, and it's doing that for those 5 seconds. Constant speed. Okay, it's very important to kind of watch and see if it's a velocity time graph or a position time graph, because again, the same portions mean different things on the different graphs. Okay, then we move on, and we have from 15 seconds to 30 seconds, the graph is going down. Okay, it's a straight line, a linear line, but it's decreasing. So what we can do is, again, look where it starts. It starts at 60 meters per minute, and it's going to 0 meters per minute. During this time portion, it is slowing down. We would sometimes say that's decelerating, but really what it means is it's a negative acceleration. You might say, Mr. Duffy, why didn't you just include till 40 seconds with that time frame? It's slowing down. The line is continuing. But once we pass 0 meters per minute, once we pass that middle point and go into the negative portion, actually what's happening is the object is speeding up again. But what it's doing though, it's speeding up in the negative direction. And so it still has the same acceleration as before, the slope's the same, but it is moving now in the negative direction, and it's speeding up in that negative direction. It's going from 0 meters per minute to now negative 40 meters per minute. Finally, the last portion of the graph, we see the line increasing again, positive slope, constant slope, is going from negative 40 meters per minute to 0 meters per minute. So negative 40 to 0, again, that means slowing down. So even though the line is going up, the object is slowing down because the line is approaching 0. I guess you can think of it that way, that if that helps you. Lines going away from 0, it's speeding up. Lines coming back towards 0, it's slowing down. I think that should help. If we have a horizontal line, again, that means constant motion. Okay, let's take a look at another useful feature of a velocity time graph is the slope of the line. Slope of the line we found in a position time graph was able to find us velocity. But again, this is a velocity time graph. So what is the slope of a velocity time graph going to show us? Well, let's remember what slope is. And slope is the rise of the line over the run, the change in vertical coordinates over the change in the horizontal coordinates. The vertical coordinates are our speed, again, or velocity. The horizontal components is our time. So what we have is the change in speed over the change in time. That is exactly the equation for acceleration. So what does the slope of a velocity time graph show us? The slope of a velocity time graph equals acceleration. Let's take a look at the different possible slopes you could have. For a velocity time graph, you could have no slope. That'd be 0 acceleration. And so what that means, 0 acceleration means constant velocity. A constant positive slope or negative slope means constant acceleration. Again, could be speeding up or slowing down, but it's constantly doing that. Finally, you could have a curved slope. That would mean that the object has a variable acceleration. The acceleration is changing throughout its motion. We will not cover that in this class. Okay? Well, that brings us to the end of the lesson. I hope it makes a little bit more sense how to represent accelerated motion, constant accelerated motion, with position graphs and velocity graphs. Thank you for watching.